Welcome to all in the lecture on types of superconductors. In the last lecture, we talked about the effect of magnetic field on superconductors. We discussed Meissner effect in detail. Meissner effect also helped us to classify the superconductors in two types: type 1 superconductors and type 2 superconductors. In this lecture, we will talk about types of superconductors and the basis by which we have classified this. We will also discuss which type of superconductors have various applications or what are the difference between these two type of superconductors here. The outline that I am following here, first we will discuss the learning outcome of the presentation, followed by student effective learning outcome. Then we will discuss the basis of classification of superconductors and how magnetic field decide this, how magnetic field can classify superconductors in the two types. We will discuss the various properties and characteristics of these superconductors, type 1 and type 2. Then we will also discuss a mixed state that is called vortex state, and in the end we will close with discussing the possible applications, exercise, and finally the references. In this lecture, we will learn about the types of superconductors and the application of these types for us. Which one is good, which one is not. And effect of magnetic field as well as transition temperature on superconducting properties. We will discuss these things in detail in this lecture. This lecture covers effective learning skills will help you to solve problems through applications of theory and practical concepts. They will also help you for critical and innovative thinking skills. Many applications have been developed like maglev trains and other behavior using this Meissner effect. You will also learn about critical thinking and analytical ability with this lecture. Many things have been developed and still it has a lot of potential. So this will be discussed in this. The classification of superconductors based on effect of magnetic field or application of magnetic field gives you idea then how the superconductors can be used even at higher temperature than transition temperature. Since the beginning of superconductors research from 1911, the biggest challenge that we are facing is about temperature at which a material gives superconducting properties. The temperature which is very low. So one of the biggest agenda for all the researchers are how to increase the temperature of superconductors. The superconductivity should survive at higher temperature. After the study of temperature, we have studied the effect of magnetic field that we have discussed in detail in the last class. Now, if you combine these both, current as well as magnetic field at temperature with temperature, then we will know that there is a possibility to increase the TC in mixed state. So we will discuss what is mixed state, what is type 1, type 2 in this lecture here. The basic properties that is used to classify the superconductors is Meissner effect. The effect given by superconductors in presence of magnetic field. Of course, when we are using the effect by superconductors, means the material already in below the transition temperature. So we have discussed Meissner effect in the last lecture, and we begin with what is Meissner effect in the next slide, then we'll move to classification. When we place a specimen, superconducting specimen, in a magnetic field, and then when we cool that specimen through a transition temperature, so at below transition temperature, when the material gives superconducting behavior, the magnetic flux originally present in the system now ejected from the specimen, and this is called Meissner effect. This was first discovered by the German scientist Meissner and Oschenfeld. On the left hand side I am showing the Meissner, and the right hand side the pic of Oschenfeld in 1933. So after 1911, the second important thing that came into picture, the magnetic field, the dramatic behavior of superconductors in magnetic field. You are having a material, you keep your material in the magnetic field. If you are not reducing the temperature, nothing will happen. But if you reduce the temperature and the material becomes superconductor below temperature, then you observe surprising behavior. The magnetic lines that is passing through this now will not pass through this, and as a matter of fact you will saw this type of behavior. All the lines will eject out like this from the system. As we have known from the Meissner effect, then if we keep a superconducting material in a magnetic field and we reduce the temperature below the transition temperature so that the material gives superconducting property, at the same time interesting thing occurred, and that thing is now the magnetic lines will expel from that material. This came to know by Meissner effect. The material will turn into diamagnetic material. The behavior is diamagnetic. It repels the magnetic field direct lines which was passing through that. This also show you one more thing, then magnetic field can be expelled, yes, but if you apply very high magnetic field, very strong magnetic field, you can also destroy superconductivity. So now we have two parameters that can work simultaneously. One is transition temperature and second is magnetic field. If your material is below transition temperature, you can apply magnetic field and magnetic field will be expelled. But even your material is below transition temperature, the magnetic field can destroy the superconductivity and can convert your superconducting material which is at low temperature into normal conductor. That threshold or critical value of applied magnetic field that is needed to destruct superconductivity, we always write or use this word as HCT, critical magnetic field, and this is always a function of temperature. It depends on temperature. So with this note that magnetic field can also destroy the superconductivity if we apply more than the sustainable value, also help us to classify the materials. First we will discuss what actually the meaning of this destruction is, then we will discuss the classification. If we plot a graph between magnetic field and temperature, then this will be the graph. This shows that if you are above Tc, the material is normal. But if you are below Tc, you can apply magnetic field. If the magnetic field is 0 somewhere here, your material is superconducting in this region. But there is a limit here on the vertical side. Only up to this it can be sustained. And this is also depend, the curvature showing this is not fixed. As you reduce the temperature, it can accept more magnetic field. But at Tc, it can't accept any magnetic field more than this. So continuously, this is your, and here, this is normal state. So you can reach to normal state by two ways, either increase the temperature or increase the magnetic field. The threshold curve separates the superconducting state in the lower left of the figure from normal state. This state is showing here magnetic field that is has a particular value for particular Tc. At the critical temperature, the critical field is 0. But as you reduce the temperature of your system below than this, critical field may be increased. So this shows that the magnetic field can destroy the superconducting behavior, and this is a very special behavior they have, like a parabolic structure. We classify the superconductor into two types, type 1 superconductors and type 2 superconductors. Type 2 superconductors have many applications, whereas type 1 has limited. Type 2 can go to little bit higher temperature than type 1. We will discuss the difference and why these two are different. What is the difference between these two? We will discuss in the coming slides. As we have discussed that magnetic field and transition temperature both are necessary to express, to study the superconducting behavior. And whenever we increase the magnetic field, two types of effects are observed. Either the material, that superconducting material gives Meissner effect properly, either it holds the Meissner effect, it exhibits the Meissner effect properly, or it exhibits the Meissner effect partially. So there are two types of materials. We can classify the superconductor into two types. One which gives full Meissner effect. Full Meissner effect means is at particular temperature and field they behaves as superconductor, and other they behaves as normal conductor, normal material. But in type 2 superconductor they are mixed. Normally what happens when we are saying partial Meissner effect, it means as the original field is reduced within the material but not wholly expelled. It can expel some magnetic field, some not, in partial Meissner effect. Whereas in full Meissner effect, all the magnetic field will be expelled. The materials like tin, mercury, they exhibit complete Meissner effect. And this effect by eliminating various chemical impurities and physical imperfections, and by choosing proper geometrical shape and size. So these are again important. What is the shape, what is the size, what are the impurities, but they can exhibit complete Meissner effect below a temperature. Below a Tc it is superconducting, above Tc it is not. And below Tc it exhibits Meissner effect, but above Tc they are not. And other superconductors like vanadium, niobium, and many other compound semiconductors exhibit only partial Meissner effect. That is, they exhibit intermediate magnetic field strength, no matter what their geometrical shape or size. In such type of superconductors, we observe a decreasing expulsion of magnetic field as its strength increases until they abruptly cease being superconductors. In relatively strong magnetic field. So the superconductive property decreases slowly. Threading will be start at particular temperature and then it moves slowly. As this was not the case with type 1. In type 1 suddenly, abruptly it moves to 0. Meissner Oceanfield have given an experiment for studying magnetic field behavior on superconductors, and this is shown here. In these two figures, which is plotted on applied magnetic field BA and the magnetic field experienced. This shows that in type 1 the change is abrupt, but in type 2 the change is gradual. Here the change you can observe here, but the here change is slowly. This is there. In type 1, the magnetic field doesn't exist after Hc, but in type 2, this is Hc, the magnetic field decrement is started below this H magnetic field, but can go up to higher, and this area is vortex state. If we apply magnetization and we plot a magnetization versus magnetic field, in this figure the applied magnetic field is on x-axis and magnetization on the y. Then some superconductors exhibit complete Meissner effect. It is shown. Complete Meissner effect means the magnetization can be shown here, but here there is no magnetization about Hc. It is called type 1 superconductors. Above critical field, the specimen behaves as normal conductor and magnetization is too small to be seen on the scale. Also keep eye here, this value is minus. Minus shows this is diamagnetic. This can be applied quantitatively to a specimen in the form of long solid cylinder. Pure specimen of many material exhibit this behavior and called type 1. This is also called soft superconductors, which can easily be converted into normal. So these are also called soft superconductor. The one more interesting thing about such superconductors are the value of Hc are always too low for type 1 superconductors. And that is the reason they are not having too much applications. Application potential is very limited for type 1 because easily they can convert into normal material. On the other hand, this is the second type of superconductors in which the flux start to penetrate the specimen at a magnetic field lower than thermodynamic critical field Hc. You can see here in the case of type 1 up to this region that I am showing here, up to this region the material shows diamagnetic behavior, but in the case of type 2 the material started from here showing normal as well as superconducting behavior, and from here to this it behaves as mixed state, and this Hc is higher than the Hc that we have chosen. It's called critical magnetic field. So from first region to this region, this is a very long region which is called vortex state, where the superconducting material lives in two forms: mixed state, and it has superconducting electrical properties. Above Hc2 it will again behave as a normal conductor. However, for a given Hc, the area under the magnetization curve is same for type 2 as type 1. You can see from here, this, if you add this area and this area will be same. The superconductors that we have discussed, type 2 superconductors, may be alloy or transition metals with high value of electrical resistivity in normal state. The electron mean free path in the normal state is short, and mean free path is involved in magnetization of superconductors. We will discuss these details in other presentations, how mean free path is involved to give superconducting behavior. So that is true that in place of single critical magnetic field Hc, we have two critical magnetic field Hc1 and Hc2. Hc1 is where the mixed state starts, and Hc2 up to which the material can give superconducting behavior, and this Hc2 is sometime 100 times or more higher than Hc. So that is very interesting. You can increase the superconducting state. However, it is a mixed state, superconducting as well as normal. As we have already discussed, the region between Hc1 and Hc2 for the superconductor is threaded by flux lines, and this state is said to be vortex state. This state has many possible applications for us. The longer that state is, you can obtain the superconducting properties even at higher sites, higher temperatures. So high magnetic field can also be sustained with this, which have many applications. This figure is showing here the variation of critical magnetic field with temperature. This gives you another information to us that yes, at Tc, material which is having higher Tc behaves as normal state. But if the material is below Tc, then up to certain state it behaves as pure superconductor, that is up to Hc1. But this region, the region between, if you increase the magnetic field even in Tc, then this region, this is called vortex state or mixed state. Both behavior exists. But you can also see the things that for temperature just below Tc, the mix is, their area is small, this region is small, but region is broadened for very small temperatures. And higher temperature, again it is normal, it behaves as a normal state. This Hc1 and Hc2 space can be increased. A lot of research we are doing to increase this Hc2 so that we can use the superconductor even at higher magnetic field. This figure is again representing the same thing in different way. Material is completely dimagnetic in the first region. In the second region, it is mixed state. In the third region, it is a normal material. So this figure is shown in terms of diamagnetic behavior, how the material is showing here. The superconducting behavior was studied in terms of Cooper pairs in BCS theory. They talked about small binding energy and the behavior of superconductors. That is true, the magnetism and superconductivity are natural enemies, it has been said. The macroscopic magnetization depends upon aligning the electrons' spin parallel to one another, while superconductivity depends on pair of electrons with a spin anti-parallel. So we will discuss the origin of this behavior in later in class, but this thing should be keep in mind. Then these are the place where we will get the answers of our queries. High Hc2, second transition where vortex state stops, is useful to develop many applications. About 410 kg or 41 Tesla has been attained in an alloy of niobium aluminum G at boiling point of helium, and 54 Tesla reported for PbMO6 acid, a compound. And this has many applications for us. We develop commercial solenoid bound with a hard superconducting produce high steady fields over 100 kg. Hard superconductors is another name of type 2 superconductors. These are called hard because it is not easily convert into superconductor to normal conductor, and has many applications. One of the application is we use this in magnetic resonance imaging, MRI, medical applications. I'm giving you two exercise here. One is, as I've discussed, this can be used in MRI, magnetic resonance, in medical treatment. Try to find out and describe this and how superconductors can be used in MRI, why it is needed and how it can be used. I'm also giving one exercise to you to make a list of type 1 and type 2 superconductors that you know. Of course, type 2 superconductors have many applications than type 1. These are the references you can go through with this, either with this website reference, or you can also go through with C. Kettle, Introduction to Solid State Physics. Thank you. We have discussed type 1, type 2 superconductors in this lecture, and we'll also learn about how we can keep the thermodynamics, the superconducting state for a longer magnetic field. Thank you. Take care.